Hi folks, I'm going to go through the first 10 slides of the homework questions for Unit 7. I'll just kind of talk through them if you need any explanation as to what's happening. So the first one, we've got a function, and I'm going to do the derivative with a combination of product rule and chain rule. It wouldn't be too hard to just FOIL this out and do it using the just the regular basic derivative rules, but won't be too bad either doing it this way. So I've got the first factor times the derivative of the second, which is 2x, and then plus the second factor, x squared minus 9, times the derivative of the first, which is 2 times 2x minus 1 to the exponent 1, times the derivative of the inside stuff, which is 2. So cleaning this up a little bit, I have 2x times 2x minus 1 squared, and then plus 4 times x squared minus 9 times 2x minus 1. So this might actually save me from having to factor a cubic or a bigger polynomial in my derivative versus if I had FOILed this out. So I'm going to factor out 2x minus 1. I'm actually going to factor out a factor of 2 as well. So then here I have x times 2x minus 1. And here I have plus 2 times x squared minus 9. So I have 2x minus 1. And here I get 2x squared minus x plus 2x squared minus 9. So I've got 4x squared minus x minus 9. And I don't think that factors that quadratic. So f prime at x equals 0 for x equals 1/2. And also, I may be missing something. Maybe it does factor. So 1 plus or minus the square root of negative 1 squared minus 4 times negative 9. Nah, this is not going to be nice unless I made a calculation error somewhere. So that would be 1 plus or minus square root of 145 over 8. And you can figure that out as a decimal. I think I would personally leave it exact unless it was a word problem though. So those are the zeros of the derivative of that function. So the question here was for 4a, and that's this one here. We want to find the critical points and then determine whether those critical points are maximum, minimum, or neither, and then find the x and y intercepts and sketch the graph. That's a bunch of stuff. The first step here is to find the derivative. So I have 4x cubed minus 16x, and I'm going to factor out a 4x, so I get x squared minus 4, and then difference of squares. So the critical numbers would be 0, x equals 2, or x equals negative 2. And where this doesn't exist, there's not any restrictions there. So I'm going to figure out intervals of increase and decrease here. So I'm going to look at the interval negative infinity to negative 2, negative 2 to 0, 0 to 2, and 2 to infinity. And I've got a 4x and an x minus 2, x plus 2. So that will give me kind of summarize into y prime and what that means about our original function. So 4x is going to be negative when x is negative and positive when x is positive. X minus 2 is negative until x gets bigger than 2. X plus 2 is only negative before negative 2. And even these little negative numbers, if you add 2, they go positive. So that tells us that the sign of the derivative can be there. And we've got a function that's decreasing, increasing, decreasing, increasing. So we have a min at x equals negative 2, and then a max at x equals 0, and then a minimum at x equals 2. So if we look at what the values would be, especially for sketching, I'm going to want to actually substitute in these values into the original function. So if I have negative 2 squared, or negative 2 to the exponent 4, pardon me, minus 8 times negative 2 squared, it's going to be 0. And if I put in a positive 2, then I would also, actually that's not, I don't know what I did there. Oh, minus 8 times 2. Pardon me. So this would actually be, sorry about that, that's negative 16, and so would that. So those are the max min points, and there's the intervals of increase and decrease. So the x and y intercepts. So for number 4, looking at the x and y intercepts, we know we've got y equals x to the 4th minus 8x squared. I would common factor an x squared, and then I get x squared minus 8. And this isn't something we would typically do for regular factoring, but I think that making that a bit of a difference of squares helps us see the zeros, x equals 0, and x equals plus or minus root 8. So when I do the graph of that, that's about 2.8 for my graph only. I wouldn't actually round that off, but just so I know about the graph or doing a sketch. And the y-intercept, of course, will be that 0. So here, if I go and just kind of do a quick sketch, and this does not have to be any kind of real detailed sketch. Like, we're not going to get really a good scale here, but we can get the shape of it for sure. So here I've got a maximum, a local maximum at 0, 0, and local minimums at negative 2, negative 16. I'm just not going to put a scale in my y, and then 2 and negative 16, because I can't really fit that. And then I would have an intercept at negative root 8 and positive root 8, and that this would go something like this. That's a maximum point, so it's going to go down there and be symmetrical, and there's the x-intercepts like that. So that's the rough sketch anyway of x to the 4th minus 8x squared. So for number 14, these were asked a couple different places. We want to make a rough sketch of the derivative function. So for A, this one is actually a line. So this is going to have the same slope. So the instantaneous rate of change is equal to 2 for all of the points on the line, right? This is just a consistent line. So the derivative function is a constant value of 2. So f prime at x just equals 2, because we can identify the slope of that line right from my graph there. For part C, if we were looking at f prime at x, we don't necessarily know a good scale here, but we do know that the slope of the tangent at the max and min points would be 0. So I'm going to put zeros here. And for these sections, let's say here, f prime at x is negative. So it's less than 0 because this is decreasing. And here it's less than 0 because it's also decreasing. And then in the middle, it's going to be positive. So for this middle section, we would have f prime at x as a positive value. So if I was going to go, now I'll do this in the red, to graph, it goes from the negatives into the positives, and then it goes back down, hits this 0 again, and then it goes into the negatives. So it's probably just an opening down parabola with zeros at -1 and 2. And we don't actually know that where the turning point is. So we don't actually know this point. But you should have the zeros and the direction correctly. So the next one for 2a, we're going to find the absolute maximum and minimum of this function. So here we're looking at a, we've got f at x is e to the negative x minus e to the negative 3x. So the derivative of that is e to the negative x times -1 minus e to the negative 3x times -3. Cleaning this up a bit, it's negative e to the negative x plus 3e to the negative 3x. Now I'm going to common factor out negative e to the exponent negative 3x, because that's my smallest exponent of x. Now this would give me e to the exponent 2x minus 3. So if we want to figure out where the zeros of this function, there will be no zeros from the first term. E to any exponent cannot be 0. But we could have e to the 2x equals 3, and then to figure out what my x value is, I would take the natural logarithm of both sides. So here I would have 2x ln e equals ln 3, and we know that the natural log of e is just 1, so I'd have x equals ln 3 over 2. So then I would take that and substitute in and figure out where the actual absolute max and min would be. So here, this is on the interval 0, 10. I would find f at 0, f at 10, and f at ln 3 over 2. That would be a potential turning point. So f at 0 is going to be 0. F at 10, I'm just going to, on your calculator, make sure you know how to use your e to the x button. So that would be e to the negative 10 minus e to the exponent negative 30. And that's really, really little, 0.000045399. Like that, really little. And I'm guessing that this would be a maximum, but let's figure this out. So I'm just going to kind of, for simplicity's sake, this is about 0.5493, and I'm going to do that as my exponent. So here I have e to the exponent negative 0.5493 minus e to the exponent negative 3 times 0.5493, and I get 0.38. So this is the max, and this is the minimum on that interval. So very similar here, we want to figure out how we would determine the extrema on this interval. So our first step is always the derivative. This is to explain your steps, but I feel like if I just do it, that's probably good. So 1 minus e to the 2x times the derivative of the exponent. So 1 minus 2e to the 2x. So where does the derivative equal 0? And it wouldn't fail to exist anywhere, but we can kind of consider that. So if the derivative equals 0, then 2e to the 2x would equal positive 1. E to the 2x equals 1/2. And then taking the natural log of both sides, ln e to the 2x equals ln of 1/2. And then 2x is ln of 1/2. So x is, because of course over on this left, ln e is just always equal to 1. So this would be ln of 0.5 divided by 2. So then I would calculate f at -2, f at +2, and f at the ln of 0.5 and divide that by 2. So we can put that into a calculator. -2 minus e to the exponent 2x would be -4. So this is about -2.02. And then 2 minus e to the 4. That is big, -52.598 about. And then we could, again, I'm just going to kind of do ln of 0.5 and then divide my answer by 2. And that's -0.34657, just so I don't get bogged down with the, this won't be an exact value, of course. So I get, putting this into my calculator, so 2 times this decimal, in that exponent on e. So I get -0.846. So this would be the max, and the minimum would be at the endpoint at 2. Here we're trying to find the local maximum between -pi/2 and pi/2 for this function y equals 2x minus tan x. So here my derivative would be 2 minus secant squared x. So we want to find where y prime equals 0. And in this interval, we would not have any restrictions on secant squared. Secant would not exist when cos was 0, but because these are not equal to, we've just got secant is restricted and doesn't exist at pi/2 or -pi/2, but we can say because it's not less than or equal to, in those inequalities, we'll just consider where y prime equals 0. So here we would get secant, we've got secant squared x equals 2, so 1 over cos squared I don't know why I'm switching to a theta there. Cos squared x equals 2. 2 cos squared, keep wanting to put a theta. 2 cos squared x equals 1. And cos x equals, this would be plus or minus root 1 over 2. So this would be the related acute angle here would be x as pi over 4. And that would be plus or minus, so it could be in any quadrant. So we would check x is pi over 4 and x is negative pi over 4, because those are the only ones in this interval where that would occur. So, and I know I would have restrictions on this function that it would be not defined at pi over 2 or negative pi over 2. So I could find the y values here. So here I would have pi over 4 times 2 minus better make sure I'm in radians. Tan of pi over 4 is 1. I don't know why I'm using a calculator here. So I've got up here and down here. So this would be 2 times pi over 4 minus tan of pi over 4, which is 1, which is just pi over 2 minus 1, which would be about 0.57. And then the negative pi over 4, we could look at that. And this would be 2 times negative pi over 4 minus, and now I get minus negative 1. So this would be 1 minus pi over 2. So we would have turning points here at negative 0.57 and positive 0.57. So that would be the max. So this one, let f and g be continuous and differentiable functions on the interval between a and b. If f and g are both increasing and f at x is less than 0 and g at x is less than 0 for all values, is the product increasing, decreasing, or neither? Okay. So it might help to just kind of wrap your head around it by saying that these are increasing functions but negative. So if I've got, let's make this interval, doesn't actually matter what the x values are. So I'm going to make some kind of general interval from a to b. And my two functions are increasing the whole time, say there, but they're negative the whole time. Okay, so we can say that I think kind of like looking at this, we would have that f at x1 is less than f at x2 for x1 less than x2, and also g at x1 is less than g at x2 for x1 less than x2. So we've got our y values of each function, but what's going to happen if we go and multiply these? So if I take these two negatives and multiply them, I would actually get, let's say, f at x1 times g at x1. that's going to be a positive value. And if I take, just to kind of explain this, if I take, and this is going to be positive too, f at x2 times g at x2, that's also going to be positive. But if I had big negative numbers, let's say negative 15 and negative 10, that would equal positive 150. But if these numbers were bigger negative actually means a smaller absolute value. So this might be like negative 3 and negative 2. So when you multiply those, you get 6. So I'm going to say that this is actually going to be, the product of f and g is going to be decreasing. Because if we kind of flip this around, we could say that negative f at x1 is bigger than negative f at x2 if x1 is less than x2. So if we kind of flip this and did like the negative of these functions, they'd actually be increasing. So because the functions, if we kind of took these, if we flip them up, they would be decreasing functions if we did kind of like the negative of each one. Like if we had the negative of these, they would be two decreasing functions if we kind of did the mirror image and multiplied each function by a negative. So we could say negative f at x is greater than 0 and negative g at x is greater than 0. For all of these, they would always be positive if the regular functions were always negative. And we could say that negative, so f times g is actually equal to negative f at x times negative g at x. That's very squished in there. So here we have two decreasing positive functions. And if you multiply two decreasing positives, that will definitely be decreasing. So the absolute value, f times g, is decreasing. And it's because you could take the negative of each one and state that those are decreasing functions. And I'm going to try and write this a little bit more clearly. That we could also say f at x times g at x is the same thing as negative f at x times negative g at x. So now here we would have two positive decreasing functions. And when you multiply positive numbers that are decreasing, you'll definitely get numbers that are decreasing. So this would be a decreasing function. Because if you multiply two negatives, it's the same as multiplying the two corresponding positive values, and those absolute values would be decreasing. So here we've got a function with this derivative, f prime at x, and we don't know the original function. We want to determine the values of x for which the function is increasing and where it's decreasing. So we're going to state our critical numbers. We want to say where is f prime at x equal to 0. That would be x equals 1, x equals negative 2, and x equals negative 3. And f prime at x doesn't exist. No values we have to think about. So I'm going to look at my intervals and make a chart. So here we're going to go from negative infinity to negative 3, negative 3 to negative 2, negative 2 to 1, and 1 to infinity. And I'm just going to consider each factor, x minus 1, x plus 2, x plus 3. So what does that tell us about the derivative, and what does it tell us about the actual function? So here, x minus 1 is going to be negative until you get to numbers that are bigger than 1. X plus 2 is going to be negative until you get numbers that are bigger than negative 2. And x plus 3 is going to be negative until you get numbers that are bigger than negative 3. So here this tells us that the first interval is negative in the derivative, so it's a decreasing function. Second interval is positive, so that's an increasing function. The third is negative, so it decreases again. And the fourth is positive, so it's increasing. So increasing would be on the intervals negative 3, 2, negative 3, negative 2, and 1 to infinity, and decreasing from negative infinity to negative 3, and between negative 2 and 1. This one, sorry, I have to kind of check. I don't know what the question's asking. Rise speed 178, number 5. Okay, so we want to determine critical points and whether they are local max or min. So we'll take our derivative here. F prime at x is 1/3 times the stuff inside to the exponent negative 2/3 times the derivative of the inside stuff. Cleaning this up, we get 2x on top over 3 times the cubed root of x squared minus 1. And I think I'm going to kind of difference of squares this guy inside. So the critical numbers are f prime at x equals 0, so that would be x equals 0, or f prime at x does not exist, and that would be x equals 1 and x equals negative 1. So I am going to take this and set up a chart to kind of analyze this. So I've got the interval negative infinity, negative 1, negative 1 to 0, 0 to 1, and 1 to infinity. And my factors, 2x, x minus 1, and x plus 1. I don't really have to consider that 3 or the cubed root. They're not affecting the sign of my derivative. So 2x is negative when x is negative and positive when x is positive. X minus 1 is negative all the way until you get a bigger number than 1. X plus 1 is only negative before you get to negative 1. So this gives me a negative overall or a decreasing function. This one here gives me positive overall and an increasing function. And here we've got a negative overall, so a decreasing function, and positive overall, so an increasing function. So here we would have, this is a little bit tricky. Are these maximums or minimums? Normally we would look at this and say this for sure is a max because this came from the derivative equaling 0, not where the derivative didn't exist. Typically where the derivative doesn't exist, that might be an asymptote. It might be a discontinuity. It might be something that's not defined on the function. But these are defined. These are no derivative, but they are defined in the function. Like we could have f at 1 would just equal 0, and f at negative 1 would just equal 0. So this is actually a min at negative 1, 0, and a min here at negative 1, 0, and a max would be if we put in x equals 0, that we would come up with that max. And I'm just going to switch over to Desmos and see if we can Desmos this guy up just to confirm what's happening here. I'm not liking that maximum there. Oh gosh, you know what? I need to double check what I did here. So this is going to be 1 and -1. I'm actually getting that this is still negative and this is still positive. I think I have maybe mixed up something in here. Yeah, this x squared minus 1 would be okay, I need to stop this. I will fix this up and edit it out of the video. But I think I made an error somewhere in here, and I just need to kind of take another look, because this shouldn't be happening, because I'm getting a max of here like 0, -1, and that doesn't make sense. So this I don't think is actually correct, and I just have to double check that.